Hello there. In this video we're going to give a brief introduction to the gamma function, which has several applications to several different fields: physics, probability, statistics, fractional calculus, and so on. So the definition of the gamma function is as follows. Gamma of x is defined to be equal to the improper integral from 0 to infinity of t to the power x minus 1 times e to the minus t dt. So here t is a dummy variable that ranges from 0 to infinity, so this is indeed a function of x. So in this video we'll discuss some properties associated to this integral defined function. Alright, so notice that this is an integral defined function, and it has two primary components. It has a polynomial part, assuming that, for example, x minus 1 is a integer, or positive integer, and it also has an exponential portion. So one method of integration that we can apply is integration by parts. So what we can do is we can let u be equal to t x minus 1, and we can let dv be equal to the remainder, e to the negative t times dt. So if this is true, then the derivative of u with respect to t is going to be equal to x minus 1 times t to the x minus 2 dx, well dt I mean. And v is going to be equal to negative e to the minus t. So this is our integration by parts relationship. So that means gamma of x is going to be equal to uv evaluated as t goes to infinity and as t goes to 0 minus the integral of v du. So as t goes to infinity, our exponential is going to go to 0. And as t goes to 0, tx minus 1 is going to go to 0. And you can verify those via L'Hopital's rule if you wish. So, at least for the infinity portion. So this leading coefficient term is going to go to 0. If we look at the other part, x minus 1 is a constant with respect to the integral t, so we can factor it out. So we have that gamma of x is going to be equal to x minus 1 times the integral from 0 to infinity of t to the x minus 2 e to the minus t dt. So if you observe what we have here, this is pretty much the same exact thing, except the exponent is now decreased by 1. So what we can say is that this is the same thing as gamma of x is equal to x minus 1 times the integral from 0 to infinity of t x minus 1 minus 1 e to the minus t dt, which is the definition of the gamma function, but evaluated at one less x value. So we have the relationship that gamma of x is going to be equal to x minus 1 times gamma of x minus 1. So this is a recursive relationship for gamma. Or we can replace x with x plus 1 and get the more common form, namely gamma x plus 1 is equal to x gamma x. So using this relationship, we can get our second property. So if gamma x plus 1 is equal to x gamma x, then that means gamma x plus 1 is going to be equal to x times, so we're going to apply the recursive relationship to gamma x, so that's going to be x minus 1 times gamma x minus 1 We can apply the recursive relationship to this. So we can say gamma x plus 1 is equal to x times x minus 1 times x minus 2 times gamma x minus 2. And we can continue this downwards. So that means gamma x plus 1 equals x times x minus 1 times x minus 2 times x minus 3 downwards. So if x is, say, a natural number, then eventually this will stop at 1. So if that is the case, then this expression here is the factorial function. So if x is a natural number, then gamma x plus 1 is the same as x factorial. And factorial has a lot of expressions in various realms of mathematics that you may know already, so this becomes the first interesting observation. All right, so what exactly does the gamma function look like? So gamma function equals 0 to infinity tx minus 1 e minus t dt. So you can verify via several properties for convergence, but the graph of this is primarily going to look similar to the following. So it has a vertical asymptote at 0. I'm not really going to discuss what goes on to the left of the vertical axis, but some interesting things happen. So we have a couple values here. 1 and 2 are of primary interest because at those values it's going to be equal to 1. So at x is equal to 3, it's going to be equal to 2, and so on. Because this is related to the factorial function. So gamma of 1 is equal to 1, gamma of 2 is equal to 1, is equivalent to saying 0 factorial is equal to 1 and 1 factorial is equal to 1, because the relationship between gamma and factorial is a shift value down. So we can say that gamma of 3 is the same as 2 factorial, which is 2 times 1, which is equal to 2. And also gamma of 5 is going to be equal to 4 times 3 times 2 times 1, which is going to be equal to 24. So a very common misconception, or thing that a lot of people get confused about, is that gamma is an analytical extension of factorials. That is, the derivative of, say, the function gamma x exists since gamma is differentiable and moreover continuous, whereas the derivative of x minus 1 factorial, which is just the same thing as gamma x for natural numbers, does not exist since factorials are only defined on the positive integers, or the natural numbers together with 0. Hence not continuous. Anywhere. Because it's a discrete function. Alright, so with those things, what other special properties can we sort of come up with? So let's consider the following. So example, what is the value of gamma of 1/2? So if we use the definition, this is going to be equal to the integral from 0 to infinity of t to the 1/2 minus 1 times e to the minus t dt. And 1/2 minus 1 is a negative 1/2, so this is the same as the integral from 0 to infinity of t to the minus 1/2 e to the minus t dt. So what I'm going to do is I'm going to get rid of this expression here. So I'm going to let t be equal to u squared, which is a symmetric function. So dt is going to be equal to 2u du. So when t is equal to 0, then that means u is going to go to 0. And when t is equal to infinity, or approaches infinity, then u is also going to approach infinity as well. So our integral then becomes the integral from infinity to 0, actually 0 to infinity, of u squared raised to the power of -1/2 times e to the minus u squared 2u du. So this expression is just u to the minus 1, so we can rewrite that as the integral from 0 to infinity of u to the minus 1, e to the minus u squared 2u du. So we know u times u to the negative first times u is going to cancel to 1. So this is just going to be equal to 2 times the integral from 0 to infinity of e to the minus u squared du. So in case you do not already recognize this integral on the left-hand side, this is what we usually refer to as the Gaussian integral. And if you haven't already seen the other video for where I prove this using multiple integrals and polar coordinates, I definitely suggest you check that out. So we find in that proof that this integral is precisely equal to 2 times the square root of pi over 2, which then just comes out to the square root of pi. So therefore, we say that gamma of 1/2 is equal to the square root of pi. So from this, we can get several other identities. For example, suppose I want gamma of 3/2. So gamma of 3/2 using our recursive relationship is going to be equal to 3/2 minus 1 times gamma of 3/2 minus 1, which is going to be the same as 1/2 times gamma 1/2. But gamma 1/2 we already found to be square root of pi, so this is just going to be the square root of pi over 2. Similarly, if I want to find, say, gamma of 5/2, this is going to be equal to 5/2 minus 1 times gamma 5/2 minus 1, or 3/2 times gamma 3/2. We already found what gamma of 3/2 is equal to. That's just the square root of pi over 2. So we have 3/2 of the square root of pi over 2, which is just 3 square root of pi's over 4. And we can continue in this fashion if we want to. For example, gamma 7/2 is going to be 5/2 of gamma 5/2. So it's going to be 5/2 of 3 square root of pi's over 4's, which will then be 15 square root of pi over 8. And we can proceed for all gamma expressions of the form gamma of n divided by 2, where n is a natural number. So that's just a brief introduction to the gamma function. Gamma function definitely is going to be introduced in a couple upcoming videos as well in various contexts. So definitely keep a lookout for that. But this is just some basic ideas. For example, the definition, some values of gamma, its graph, and its relation to the factorial.